Hi, Assalamualaikum. Morning again, everyone. This is my lecture 4 for CHM577. And for this lecture 4, I am going to cover Fajans Rules, which describes the covalent character of ionic bond. These lecture notes are prepared by Dr. Amalina, and I'm presenting it for my class of AS2223M1. So when I talk about Fajans rules or polarization, we are talking about how in an ionic bond or in an ionic compound, the cation may polarize the anion. So it is talking about the polarizability of an anion by a cation. Yeah, so the effect of the cation on the electron cloud of an anion. And polarizability, or the ability to become polarized. We learned about polarization in lecture 3. That means the presence of distortion or the presence of different charge from the complete or ideal shape into something else, distortion. Yeah? So polarizability of an anion is the how easy it is to distort the electron cloud of an anion. And it is caused by the presence of the cation. So when you have a cation and you have an anion that are bonded together in an ionic compound, when your cation has a high charge, for example, 2 plus or 3 plus, or it has a small size and a high charge cation, will make that cation having the power to affect the anion, i.e. to pull electrons to itself. Because if you recall, how are cations formed? Cations are formed through the element or the atom losing an electron or 2 electrons. So cations are usually lacking of electron, having a positive charge. Anions, on the other hand, has a surplus or an excess of electron, and it has a negative charge. So if a cation has strong enough positive charge and small enough size, that means the nuclear charge is felt strongly, then it can affect the electrons of the anion that it is bonded to. So the anion becomes very polarizable in the presence of high charge, small size cations. And we are saying that the polarizing power of cation is proportional to the charge and inversely proportional to the size of that cation. A small cation makes it very polarizing. A highly charged cation makes it more polarizing. So that is about cation. What about the anion? Now, anion, on the other hand, also becomes easily polarizable when it has high negative charge. That means when it has, for example, 2 minus, 3 minus, that means there are a lot of electron surplus or excess for that anions, and that excess electrons are not being held strongly by the nucleus of that anion. That means that high charge, high negative charge, and large size. Large size also means that the outer electrons are being held loosely by the nucleus. That means for anion, high charge and large size will make that anion very, very polarizable. So we talk about polarizable for anion, and we talk about polarizing power for cation. And the third factor that will increase polarizability of an anion is an incomplete valence shell electron configuration. That means when you have a noble gas configuration of a cation, contohnya, for example, sodium 2.8, that is a noble gas configuration, it provides a better shielding and less polarizing power of that cation. But if you have an incomplete valence shell configuration, for example, for the transition metals, then you are going to make the anion it is attached to be very, very polarizable. Contohnya, for example, a charge factor, the charge factor that we are talking about in here, the charge factor is the effective nuclear charge. How do we know the effective nuclear charge? Look in the periodic table. How do we know? Just look at this periodic table. Just make it bigger a bit. I'm sorry about that. Yeah. So if you want to know how many what is the nuclear charge of any element, you look at the atomic number, because the atomic number coincides or is exactly the same as the number of protons in the nucleus. And the number of protons in the nucleus is the nuclear charge. So if you look at, for example, mercury, Hg2 plus, Hg2 plus is here. It has 80 atomic number. Atomic number of 80 represents 80 protons in the nucleus of a mercury. So that means the nuclear charge of mercury is very high, 80 plus. Compare it with calcium. Calcium only has 20 protons in its nucleus. So the nuclear charge of calcium is only 20. So comparing, go back here, comparing between, make it smaller a bit. Excuse me. Okay, comparing between mercury 2 plus and calcium 2 plus. Why do we compare these two? Because they have very, very similar sizes, 102 picometers and 100 picometers, very similar sizes, but very, very different nuclear charge. You will find that mercury is a lot more polarizing compared to calcium, because the polarizing power of something with a complete noble gas configuration will provide better shielding and less polarizing power. So your transition metals, when you are comparing it size with a representative metal cation, you're always going to find that the transition metal cations are more polarizing than the representative metal cations because of the higher effective nuclear charge. Yeah, the pull from the nucleus is a lot bigger for uh, um, transition metal cations. We're going to go through this a little bit later in the coming few slides. Now, Fajans rules were formulated by a Polish-born chemist called Casimir. Some reference spell his name as Casimir. Some reference spell his name as Casimir, but same. And his surname is Fajans, in 1923. He was working on this between 1923-24, and these rules govern the degree of non-polar character or covalency that is present in ionic compounds. Because we all know for ionic compounds, you have a complete transfer of electrons from the cation to the anion. However, depending on the relative sizes and relative charge of the cation and anion, some of these may not be complete ideal ionic situations. Some of them may have a little bit of covalent character. So we're saying the covalency of some ionic compounds is governed by the Fajans rules. Now, looking at these three pictures at the bottom, theoretically, the bonding of the compounds below, they are purely ionic. This is the pure ionic then. It is an attraction between the positive and negative ion, just like this. This is your cation, that is your anion, and usually anions are much bigger than cations, yeah, as we cover in lecture number 1. However, in practice, electrons of negative ion or the anions can also be attracted towards the positive ion or the cation and becomes distorted in shape, resulting in some degree of covalent character or some degree of electron sharing. Now, this is an ideal case of an ionic compound. Yeah, this case on the left-hand side here is the ideal case of ionic compound there. Excuse me. And when you have the cation becoming smaller, remember the polarizing power of a cation decreases with size or increases as the cation becomes smaller. When the cation becomes smaller, it has more power to pull electrons from the anion towards itself. So the anion becomes polarized by the cation. And maybe sometimes the cation also undergo a little bit of shape distortion or polarization, but only slightly. So we are saying in the case in the middle here, sorry, excuse me, in this case in the middle, yep, this case here, the anion is getting a little bit more polarized because your cation becomes smaller, and it's described as ionic bond that has some covalent character, because we all know covalent is all about sharing. Ionic is all about complete transfer. Now, this is ionic bond that has some covalent character. But when there is more polarization happening, especially on the anion and also on the cation, we are saying that the anion and the cation become both polarized and they share covalent bond. Even though you have cation and anion, they may share covalent bond. I'm going to give you some example. For example, you have I don't know, very small cation, very large anion will produce something like this. For example, aluminum iodide. We're going to go through that in a while. Aluminum iodide, right? Now, if you recall our lecture 3, Linus Pauling dealt with variation in polarity in terms of degree of ionic character in covalent bond. For Linus Pauling, his focus is on covalent bonds and how much ionic character is present in the ionic bond. However, Fajans approach it differently. He looked at ionic compounds and how much covalent character is present. So both scientists are looking at similar things from different angles. So Linus Pauling looking at covalent bond with ionic character, and contrary to that, Fajans looking at ionic bond with covalent character in terms of polarization effect. So Fajans rules focus on the size and charge relationship between the cation and the anion, how the cations are affecting the anion when the sizes and the charges are varied, and the electronic configuration of the cation. So when you look at it, charge density or polarizing power of the cation is charge over size, and this is the formula. Polarizing power of a cation is Z plus divided by R plus, where Z is the nuclear charge and R is the radius of that cation. the charge of the cation and the radius of that cation. So when we are looking for ionic character of a compound, we always look for low positive charge. Remember, ionic character is complete transfer, no sharing. So we look for low positive charge of the cation, a large cation, and a small anion. Large cation means it just cannot pull electrons from that anion. But when you look for covalent character, you are always looking at high positive charge of the cation, because high positive charge actually has more pull or more attraction for the electrons in the anion. Small cation, again, very, very strong nuclear presence, nuclear charge presence there, and a large anion. So for anion, the size has to be large to be easily polarizable, whereas a small anion will be less polarizable. But for large cation, it will not be able to pull electrons much from the anion. So this is the relationship. Just remember this formula here. Okay, there will be more. So for cations, non-polar or covalent character increases with decreasing cation size and increasing cation charge. Very small cations or any cations with high charge density consequently tend to distort or polarize the electron cloud around an anion. This is the same thing. I'm just saying, I'm just describing it differently now. Uh, uh, the stronger the pull for electron of your cation, the more easily it is for the anion electron cloud to be distorted. The greater the polarization of the anion, the more non-polar or the more covalent is the bond between the atoms. That is when we look at it from the point of view of cations. But when you look at it from the point of view of anions, the non-polar or the covalent character increases with an increase of the anion size. The bigger the anion, the more easily it is to become distorted. Can you imagine if you have a big electron cloud, it is easier to pull it apart, to make it differently shaped. And then the anionic charge. The larger the anion, excuse me, or the higher its negative charge, the more easily it is to be polarized by the cations, because the electrons of the anions are held more loosely. For anions that are big or anion with big negative charge, the electrons cannot be held strongly by the nucleus, so it's easily polarizable. Yep. So this is just again saying the same thing in a different way. Uh, uh, the Fajans rule are saying that an ionic compound is more likely to have some covalent character if the cation is small, highly charged, or when the anion is large and highly charged. So the difference here is actually between the sizes and the charges. So highly polarizing cation is for small cation and highly charged cation, whereas highly polarizable anions are large anions and highly charged anions. So for anions that are large and highly charged, it is highly polarizable and electron cloud will be easily distorted. So this is the picture that is represented by the explanation. So I have changed it slightly from the slide that you have. So you may want to write this rewrite this title to make it more understandable. The title should be the non-polar or covalent character of cations with non-noble gas electron configuration. Now remember, the cations, when they are formed, for representative metals, they will become having the configuration of noble gases, whereas the transition metals, when they become cations, they do not become like a noble gas configuration. They just lose electrons like that. So cations with 8 electron structures will cause less distortion. Why? Because of the complete shielding. The complete shielding, because you have the octet outside. That means it undergoes less distortion themselves than those with 18 electron structures. When we talk about 18 electron structures, we are talking about transition metals because they are pseudo noble gas structures. Yeah. So if we compare cations of about the same size, we can compare between sodium plus and copper plus. They have the same size. Sodium plus is 0.95 angstrom, whereas copper plus is 0.96 angstrom. Very, very small difference in size. But the pseudo noble gas or the transition metal or the copper has higher nuclear charge than the sodium plus. If you look at the sodium plus, the number of protons is 11 because the atomic number is 11, whereas copper, the number of protons is 29 because the atomic number is 29. So copper has higher nuclear charge than sodium. That means copper has more polarizing power compared to sodium. So copper with a pseudo noble gas electron configuration has more polarizing power than sodium plus with the noble gas electron configuration less polarizing power. This is the non-noble gas electron configuration for copper. Ar, argon, 3d10 for copper plus, whereas sodium is simply neon, is exactly like a noble gas. So the shielding is much more effective in sodium. Yeah, that is why copper is more polarizing than sodium because of the higher nuclear charge of copper compared to the sodium. Right, an anion near copper plus ion, when you compare it with a sodium plus ion, the anion will behave as though it was under the influence of a greater ionic charge, and it will become distorted to a greater extent because copper will distort that anion. If you, for example, talk about chloride, yeah, chloride. When chloride anion is seated next to a copper plus, it will become more distorted if you compare it with when it's seated next to a sodium plus. Yeah, the spherical d electron cloud of copper is also more easily polarized by anions than the 8 electron shell of the sodium. So this results in some polarization of a pseudo noble gas cation by the anion also. So not only it is more polarizing, it is also more polarizable, copper, when you compare it to sodium because of the factors that I explained earlier. So higher polarizing power of copper plus is due to the higher effective nuclear charge of that ion, cation. So covalent characteristic. Now the physical properties of ionic compounds are very, very prominent. All ionic compounds have very, very high melting point, very high boiling point. That is why it is difficult for you to melt a salt, for example. It has very high solubility, it has very high conductivity when you compare it with any covalent compound. So, Fajans described that as covalency in any ionic compound increases, the solubility will decrease because a covalent compound will have low solubility in water. Yeah? The solubility will decrease and melting point will also decrease because the melting point of a covalent compound is always lower than the melting point of ionic compound. Therefore, covalent character increases with increasing size of the anion. Now, if you compare the anion of sulfur with anion of oxygen, we know that sulfur is bigger than oxygen. So MgS is less soluble than MgO. Magnesium, you make it constant, you combine sulfur with magnesium, you combine sulfur with oxygen, you compare the two, and you look at the solubility, and it is always MgO more soluble than MgS, because solubility is the characteristic of ionic, whereas non-solubility is the characteristic of covalent. So anything with high covalency will be less soluble. So MgS, because of the large size of sulfur, because of the high polarizability of sulfur, will be less soluble than MgO. And then another thing you look at is the melting point. Covalent character also increase with decreasing size of the cation. So when you compare, excuse me, right? When you compare between beryllium chloride and calcium chloride, beryllium is obviously smaller than calcium. So you're going to find that the melting point of calcium chloride is higher than the melting point of beryllium chloride. That is saying that beryllium chloride is more covalent in character when you compare it with calcium chloride because of the small size of the cation. That means it is more polarizing compared to calcium. Calcium is less polarizing. So less polarizing means more ionic. More polarizing means more covalent. Anything covalent will have lower boiling point and melting point. So you have BeCl2 has lower melting point compared to CaCl2 because of the polarizing power of beryllium. And Fajans also described that as covalent character increases, the covalent character increases with increasing charge of either ion. If both the ions, either the cations or the anions, have high charge, cation will be highly positive, anion will be highly negative, then you are going to have more increasing covalent character. For example, FeOH3 is less soluble than FeOH2 because Fe3 plus has high charge. In here, it is ion 3 plus. In here, it is ion 2 plus. So ion 3 plus has a high charge, thus it has a high polarizing power than ion 2 plus. That means it has more covalent character. So more covalent character, that means it is less soluble in water. And we're talking about solubility in water here. So another thing that Fajans describe is that covalent character is greater for cation with non-noble gas configuration. As I was explaining to you earlier, the non-noble gas configuration actually refers to transition metals. So transition metals are generally less soluble than alkali or alkaline earth metals. The melting point of mercury chloride is 276, low, whereas the melting point of calcium chloride is 772, high, indicating in high ionic character or low covalent character of CaCl2 and high covalent character of mercury Cl2 due to the high polarizing power of your mercury 2 plus. So in conclusion, for Fajans rule, for any given cation, covalent character increases with increasing anion size. For any given anion, covalent character increases with decreasing cation size. However, the covalent character increases with increasing charge on either of the ions. So the covalent character is greater for cations with non-noble gas electron configuration. Yeah. transition metals. So a greater covalent character resulting from a soft interaction is related with lower solubility. When we talk about soft, we're talking about highly polarizable, big anion, big cation. Yeah, that is soft. When we talk about hard, that means small anion, small the highly charged cations. Yeah, so the covalent character resulting from the soft interaction is related to lower solubility, related to color, short inter-ionic distance, whereas hard interaction results in colorless and highly soluble compound. Always ionic compounds are highly soluble, and you quite rarely get colored compounds there, because colors are actually due to the jumping of electrons. I mean, this will be covered a little bit later in the semester. Don't worry about the colors. Just remember that hard and soft interaction is very much to do with polarizing power and polarizability. Yeah. So, for example, there are A, B, C, D, E, F, G, H, 8 compounds here. Predict which one is more covalent between SbCl3 and bismuth Cl3. So all you have to do is look at the size, look at the charge. Excuse me. The charges are the same because they are all 3 plus for the stibbium and bismuth, but the size is different. Bismuth is a lot smaller. How do I know it is a lot smaller? Let's have a look at the periodic table. Where is my periodic table? Just 1 second. I think periodic table is here. Yeah, let's copy that. Copy here and bring it here. Bring it. Excuse me. I'm making you dizzy now. Bring it here. Yeah. Yeah, looking at SB. Making it bigger. What is stibbium? Stibbium. Oh, I can't find it, honestly. Stibbium, SB. Who can find stibbium? Ah, there you go. That's stibbium. It is on the 1, 2, 3, 4, fifth shell. Whereas bismuth, what is your bismuth? There. Oh, bismuth is bigger. So bismuth is bigger than stibbium. So bismuth is less polarizing compared to stibbium. Stibbium is smaller than bismuth. So SbCl3 is more covalent. In here, you have the difference is between oxygen and sulfur. You have your oxygen smaller than your sulfur. Sulfur is larger than oxygen. Therefore, BeS, beryllium sulfide, is more covalent. Now, tellurium, you have Tl2O and Tl2O3. The difference is the charge. So, tellurium, Tl plus compared to Tr3 plus, we're talking about the difference in charge. So, not tellurium, thallium. Thallium plus and thallium 3 plus, you're going to see that the thallium 3 plus is a lot more covalent compared to thallium plus. Yeah, this one is more covalent. And between sodium chloride and copper chloride, because copper is transition metal, copper chloride is more covalent. So that is the argument when you are comparing between these compounds. So next, I have a question for you. Between A, B, C, and D in this picture, which one is least covalent? So try to work it out. Look at the size, look at the charge, look at the position of your cations, whether it is in the representative metal or in the transition metal. Only three factors: the sizes, the charges and the type of cation, whether it is transition metal or representative metal. So I'm going to leave you there with this question, and we're going to discuss the answer outside of this lecture. So I think that is all about Fajans rule. Thank you very much for listening. This is about a 35-minute lecture, but quite short compared to the others. So see you later in my lecture number 5. Okay, bye-bye. Assalamualaikum.